I'm Dr. Dewitt, and welcome to... From this end and the bowl called... Hi, I'm Dr. Dewitt here at the National Aeronautics and Space Administration, better known to you as NASA. Welcome to the show Do It Again. Our series will present a number of demonstrations about the science of flight, or aeronautics. We'll be able to talk to real NASA experts about our demos and also hear about their exciting aerospace careers. We'll finish out our program showing you a new NASA website and some fun activities that you can do in your class or at home. So let's do it. Our special audience is with us today. They're from Armstrong Elementary School, but they're not here in my lab. They are at the Virginia Air and Space Center in Hampton, Virginia. They're connected live to us on the internet through video conferencing. Hello, students from Armstrong Elementary School. This show is all about the forces involved in flight. The forces consist of pushes and pulls. There are only 4 forces involved with flight, and to help you understand terms that you'll hear during the show, let's go find out more from Notron, our knowledge bank. So Notron, what do you have for us? The first force is gravity. That's the force that pulls us down towards the Earth. Our next force is drag. That's a force that opposes the motion of an object through the air. Our next force is lift. That's the force that works opposite to gravity. And thrust is our final force. That's the force that pushes things forward through the air. Now, these are the 4 forces that you need to understand to appreciate how animals and humans and insects are able to fly. Let's take a look at how it all started.
Since the days when humans first watched birds, the desire to fly has been with us. The most successful groups of living things that fly are insects, birds, and bats. The extinct Pterosaurus, an order of reptiles living back during the dinosaurs, were also very successful flying animals. Some 350 million years ago, when there were only 2 major land masses, insects began flying. How and why insects' wings developed, however, is not well understood. One theory is that insects developed wings over time as a result of jumping off branches to escape predators. The glands on the insect might have served as parachutes, letting these insects land more softly. Bats are the only mammals capable of sustaining level flight. However, there are several gliding mammals able to glide from tree to tree using fleshy membranes beneath their limbs. Some can travel hundreds of meters in this way with very little loss in height. Among living animals that fly, the albatross has the greatest wingspan, up to 3.5 meters or 11.5 feet. The great bustard is the heaviest flying bird, weighing in at 21 kilograms or 46 pounds. People studied birds and sought to create bird-like structures with which to fly, but they failed miserably. According to Chinese legend, one kite was built so huge that it lifted a man into the sky, but that is just a legend. In the 1700s, the French created a hot air balloon, and for the first time, a human being was lifted into the sky. Not satisfied with floating in the air, the quest for controlled, heavier-than-air flight began in the late 1800s. Early experimenters tested devices on the sides of cliffs, where there was a steady, natural source of wind. People flew in glider-like contraptions, but sustained flight still eluded these early daredevils. It was the Wright brothers who finally realized humankind's great dream. On December 17, 1903, Orville Wright became the first person to finally lift up into the air using a heavier-than-air craft for a powered, controlled flight. Although there were experiments and inventions by other people, the Wright brothers carefully and systematically sorted out all the data then known about flight. Testing on a cliffside had its uses, but there wasn't any way to accurately measure research test results. So the Wright brothers rigorously recorded their data and analyzed the tests they themselves ran. And they carefully evaluated their own results, whether successful or not. This was the beginning of what we today call the science of aeronautics. And using this, we can now fly around the world and to the frontier of space.
Now, this is the part of the show where we demonstrate the forces of flight. Hey, Kimiko.
Hi, Dr. Dewitt.
How are you doing today?
I'm doing great.
Kimiko is my lab assistant today. Kimiko, would you help me show the audience the four forces of flight?
Sure, I'd love to. Hi, students.
Let's start by dropping a hammer. Now pay close attention to what happens and why. Now, which force of flight is at work here?
Gravity!
Oh, you're right, gravity. As the hammer was pulled towards the ground, we could see the force of gravity acting upon it.
This time, let's drop a feather.
Good idea.
Wow, that feather behaved very differently. Was gravity at work here?
Yes, because the gravity did pull the feather down to the ground.
But there must be another force at work to cause the difference. Why did that feather behave that way?
Well, Kimiko, the force that caused the difference is drag. Drag is the force that opposes or slows the motion of an object. Let's drop these again, but at the same time. 3, 2, 1. The reason that these fall differently is because the air particles pushing up on them while gravity is pulling down on them, and the resistance of the air particles causes the feather to fall more slowly. And we call this drag.
So it's not the weight?
No, because the hammer is feeling drag too. But we could prove that if there were no air. Could we try this someplace where there are no air particles or molecules?
I know, Dr. Dewitt. We could try the experiment on the moon.
Next stop, the moon.
Well, in my left hand, I have a feather. In my right hand, a hammer. And I guess one of the reasons we got here today was because of a gentleman named Galileo a long time ago who made a rather significant discovery about falling objects in gravity fields. And we thought that where would be a better place to confirm his findings than on the moon. And so we thought we'd try it here for you. The feather happens to be appropriately a falcon feather for our falcon. And I'll drop the two of them here, and hopefully they'll hit the ground at the same time. How about that? Which proves that Mr. Galileo was correct in his findings.
So, with no air particles to slow down the feather and the hammer, they both hit the surface of the moon at the same time.
So, with gravity pulling on them, how do we get these objects into the air?
Well, let's do another demo. Let's try an experiment with this ping pong ball and that hair dryer. Would you turn the hair dryer on? Okay, now I'm going to put the ping pong ball in here and let's see what happens. Wow.
What's holding up the ping pong ball?
Well, there's a column of air coming out of that hair dryer, and it's able to stay suspended because the air coming out of the blow dryer provides lift, and the ball is able to move opposite to gravity. Let's try tilting it over and see when gravity takes over and takes the ball away from the air. That was pretty far over, wasn't it?
Yes.
We'd be happy to do it again, but as we always do, we're going to do it bigger and better. So I have a leaf blower, and you have the world in your hands. Isn't that nice? Wasn't that neat?
That was neat. Wow, Dr. Dewitt, it looks like a shark.
Well, it's because it's got the same body form as a shark, Kimiko. It's got to swim through the air just like a shark swims through the water, both of them being fluids. What do you think gives it its lift?
What, Dr. Dewitt?
Well, it's full of helium, a lighter than air gas. And the lighter than air gas will cause the balloon to rise through the air because it is lighter than air.
But an airplane's not lighter than air, is it?
No, an airplane isn't lighter than air. Lift on an airplane comes from its wings, and we're going to have a demo in just a moment to demonstrate that.
Okay.
Kimiko, we're now going to demonstrate thrust. And thrust is something that I remember from my grandmother telling me when she was a little girl, she saw a broom straw driven into an oak tree after a hurricane, the strong winds of a hurricane. Well, we have to simulate that here because we can't get a hurricane in here, can we? But I've got hurricane in a can right there. It's high pressure air. And we can't get a broom straw because I don't even think they use broom straws anymore. So we're going to use a NASA pencil because they fly fastest. And in place of an oak tree, which we can't get in here, we're going to simulate that with a block of hardwood. Could you find me the hardwood? Where did it get to? There it is. Okay, so we're going to use this block of hardwood. Don't do that at home. And we're going to put it at the end of the pencil accelerator. And then we're going to accelerate the pencil down this tube and into the block of hardwood. But first, we're going to put on safety glasses because this is a part where things might fly and we want to protect our eyes at all times. Okay, would you mount the wood? Okay, now we're going to demonstrate this thrust by pushing the air behind the pencil, which will shove the pencil down the tube and hopefully into the block of wood. Okay, now we're going to put the pencil in the pencil accelerator, and I'm going to push it in a little bit further with another pencil. And now it's come out into the clear plastic tube. We'll close the breech. And I need to know, is the target area clear?
Roger that, Dr. Dewitt. Green to go.
Excellent. Then we can turn on our air, our pseudo-hurricane. And this is a part where the audience can help us. So we need a countdown, because we always launch things with countdowns. So we're going to go 5, 4, 3, 2, 1. Are you ready? 5, 4, 3, 2, 1.
Wow, Dr. Dewitt, I guess your grandmother was right.
I think she just might have been.
But we don't shoot airplanes out of accelerators.
No, we don't. Some airplanes have propellers. And we have a demo coming up that will teach you more about how airplanes fly.
Now that looks like it can do some serious flying.
And I think it can. It's got a propeller in front, and we can hook it to this line, and the propeller actually creates a low pressure in front of the plane and pulls the plane into it, then the wings provide the lift. You ready? We need a countdown.
Okay.
5, 4, 3, 2, 1. Okay. So that was our airplane with a propeller. Now, let's do it again. What do you think this represents, boys and girls? It's a jet. Pressure's higher inside, pushes out the nozzle in the back, and makes the balloon go forward. So thrust is not just for propeller-driven craft. Thrust is also for jets. So jets work the same way, only they heat the air and compress it and then spit it out a lot better than this balloon does. So the higher pressure will come out the back and send the balloon forward. Action, reaction, Newton's third law. Are you ready?
Yes.
Another countdown. 5, 4, 3, 2, 1. Those demonstrations were fun. Remember, safety comes first, so make sure that you have a teacher or a parent to help you with any of these at school or at home. And always wear your safety glasses. Now I'd like to introduce you to our NASA expert, who happens to be an aeronautics engineer. Hey, Joe, tell us about your job with NASA and some of the work you do that involves the forces of flight.
Thank you. I work in the Research Controls and Dynamics branch here at NASA Glenn. And within that branch, I actually work on a project here in fundamental aeronautics that's called supersonics. And we work on planes that actually travel faster than the speed of sound. And specifically within that project, I work on the force of thrust. And that's basically to power the airplanes we need jet engines. And I work on the computer modeling of those jet engines to make sure that they're safe and operate very efficiently so that we can fly our planes in the supersonic regime.
All right, we've got a question from John. John, go ahead.
Can airplanes fly in space?
So airplanes don't really fly in space, and part of the reason for that is our forces of flight don't really work the same way in space. And the reason for that is our forces of flight require us to fly through some kind of fluid. And when we use the word fluid, it's a very broad sense of the word fluid. It means that it could be moving through water or it could be moving through air like our atmosphere. So boats and submarines go through the water and airplanes go through the air. But as we get into space, we don't have any fluid to move through. In space, the pressure is basically zero. We're in a vacuum. So that we don't have anything that moves over the wing to create lift. And because of that, we're not able to generate lift and propulsion the exact same way that we do when we're flying through a fluid. But what we end up doing in space is we use rockets. And part of the reason why we use rockets is because they have all the fuel and propellant stored on board. So they just let stuff out of the rocket chamber at a super high speed to allow the rocket vehicle to move around in space. But it's not really flying, it's more in continuous free fall.
And here we have a question from Cameron. Cameron?
Do skydivers actually fly?
Well, I can tell you when I actually went skydiving, I sort of fell out of the plane like a rock, just screaming all the way down. But in general, we don't really consider skydivers to actually fly. Basically, you're in free fall when you go skydiving. But some people actually have special uniforms where they're able to glide a little bit and do stunts and tricks. But we don't really consider them to be flying, we just consider them to be gliding, because if you're going to be flying, you usually have to maintain a level flight and a level altitude, and when you're skydiving, you're continuously falling and getting closer to the earth.
All right, our next question is from Paul. Paul?
Will we ever have flying cars?
Flying cars is a very interesting and very sci-fi futuristic idea, but one of the projects that I just read about recently going on at DARPA is actually looking at how to build flying cars for the military and for specifically marine outfits. And what they're actually doing is developing a flying car that looks very similar to a helicopter, but it has wheels so it can maneuver on the ground as well. and they're doing some testing of those vehicles right now. So it's not exactly the flying cars of the movies, but we could be looking at flying cars for military operations relatively soon.
Our next question is from Tiffany. Tiffany, go ahead.
How did you become an aeronautics engineer?
Well, I became an aeronautics engineer because I watched some NOVA PBS TV specials on NASA, and I became fascinated with NASA, and I just wanted to find a job where I could do something very challenging, very rewarding, and something that very few people get to work on. So in school, I started getting interested in physics and math, but eventually I got to the point where I was looking at various colleges, and no one in my family had ever really gone to college. So I didn't know how to actually become an engineer or really what an engineer did. So when I was visiting the Ohio State University and I told them that I wanted to work at NASA, and they told me that I should be looking at engineering, I actually told them that I didn't want to drive a train, I wanted to work for NASA. But they eventually informed me that engineering is where we actually go about building and designing future vehicles for space and for aeronautic applications. So that's how I found my passion in my pursuit for aeronautics engineering.
Our last question is from Donovan.
What's the world's fastest airplane?
So there's a couple different answers to this question depending on what you consider to be an airplane. So the very fastest air-breathing, basically jet airplane, where we have a normal engine on the plane, similar to the engines that you see on the commercial aircrafts and being flown by an actual human pilot, is the SR-71. That was a military spy plane, and it flew around 3 times the speed of sound. And the speed of sound is basically how long it takes for your voice to travel to your friend's ear. So you can imagine whenever you talk to someone, basically you hear them right away, and this plane would actually travel 3 times faster than that. So it's moving really fast. But there's other planes that weren't piloted by a human on board. They were piloted on the ground, and those were hypersonic planes. And we have the X-43, which flew faster than the SR-71. That was more like the Mach 6 range. And we also have a rocket plane, which was the X-15, which holds the absolute record.
Joe, I want to thank you for being on Do It Again today and sharing your expertise.
Thank you so much for inviting me. It was a pleasure being here to talk about aerospace engineering and the forces of flight.
We're almost out of time for today's show. For the teachers watching, I'd like to provide you with a brief description of NASA educational resources that can extend the demonstrations and concepts that were presented during our show.
Hello, teachers. I'm Bonnie Murray, Education Consultant for Do It Again. Let me show you some NASA resources you can use to further explore the forces of flight with your students. The science of flight includes the study of air pressure, conditions in the atmosphere, energy transfer, and many other topics that are already a part of your existing curriculum. The Museum in a Box Toolkit is packed, literally, with engaging activities that allow your students to experience these ideas in a meaningful context and more easily learn these abstract concepts. The toolkit has an entire chapter on principles of flight. Let's preview some of these lessons. 4 forces. This lesson provides detailed explanation of the forces, information about how the principles and laws work, and a game to allow students practice with the terms. Bernoulli. This lesson contains simple experiments using readily available materials to allow students to see the forces at work. Principles of Flight in Action is a challenge activity in which students use NASA's online flight simulation software to learn about the aerodynamics of flight. Kites. This lesson might be a great place to start exploration of flight concepts with your students. Each lesson has clearly stated objectives, correlation to national science and math standards, detailed explanation of the activities, and a list of necessary materials and vocabulary terms. There's background information and an assessment strategy as well. Activities are included for all grade levels, kindergarten through high school. The website for Museum in a Box is your source for a growing number of downloadable lessons about aeronautics. So check back often or sign up for the RSS feed and you'll receive notification of new lessons as they're posted. Finally, have fun. Experiment. Use the demos to promote inquiry learning and let your students explore this content with the hands-on activities. Your students will have a great time, and you will too.
The next time you look up in the sky and see something flying by, I think you'll have a better understanding of how it got up there and how it remains in flight. You'll also be better prepared for our next show that features flight testing the NASA way. Until then, for all of us here at NASA's Do It Again, we'll see you in Dr. Do It's Aero Shop.